In this video, I will talk about Ohm's law and resistance. And the basic physics or approximations of Ohm's law are shown here, where we have the volume current density to be proportional to the force per unit charge. So this lowercase f, this will be the force per unit charge. Now this the other constant, this is the conductivity, and conductivity depends on the material that your object is made from. In addition to conductivity, we also define the inverse of that. 1 over conductivity will give you the resistivity. But at the end of the day, they, of course, since they are inverse of each other, they both depend on the material, and they both describe essentially the same thing. Now, this is the basic assumption of Ohm's law. In the case where the only thing you have is an electric field that is exerting a force on your charges, then we know that the electric force is QE, which means the electric force over Q will give you the electric field, which is why if the only thing you have in an electric field, your current density is going to be proportional to the electric field. Now this is more general though. Okay, so this is the one that I want you to keep in mind. And if we have just the presence of an electric field, we're going to use sigma times the electric field. Now, using this expression, okay, typically when you work in circuits, we deal and we use the conventional current, we use potential difference, and this is why you are more familiar with this. Now, this is an expression that you can derive by using sigma times the force per unit charge. I will show you a couple of examples. This here in this expression, sigma is the conductivity, and as I mentioned before, it depends only on the material. I want to point out though that in this expression that we do use a lot in circuits, the resistance R, okay, you're familiar with R, this is a resistance. The resistance R depends not only on the material that the resistor is made of, but it also depends on the geometry. And by geometry, I mean the length, the cross-sectional area, the way with which current is flowing, in which direction the current is flowing, and I will show you two different examples of that. So in the more fundamental expression for Ohm's law, this constant depends only on the material, but when we use it in the context of potential difference and conventional current, you need to remember that the resistance R depends not only on the material, but also on the geometry. In the first example that I will do, let's say we have the current, let's say that the conventional current is flowing this way, which means the electric field inside our object is pointing in the same direction. Okay, conventional current and electric field, they always point in the same direction. And let's say A is the cross-sectional area of the wire. You have L for the length, for this segment at least. And we know that you can find the current by using the current density, the volume current density. If I assume that the electric field is the only thing that is driving the current, then this becomes E dot dA, and this is the area that I'm talking about. And of course, if the electric field is uniform, and this will be just times the area. And as I said, with the assumption that the electric field is uniform, since we know that delta V, okay, is minus E dot dl from the initial to the final, with a uniform electric field, this becomes minus E times L. I do want to remind you, this area is part of this cross-sectional area, so it will be a small segment over here, but the dl is going to be, okay, it's going to be over here in this dimension of your object, and you may choose the dl to point to the right or the left, whatever you want. But you do you need to keep in mind that the dA, the element dA is here, dl is on this side. Now, if the only thing that I'm looking for is a relationship between the conventional current and the potential difference, but only in terms of their absolute values, then what I will do is say, okay, I don't really care whether I'm doing V final minus V initial or V final minus V initial. I don't care where I place the two electrodes of the voltmeter. Then this is just E times L. And solving for E, you get the absolute value of delta V over L, which I can use here. Let's say I'm gonna move on. This is equals to sigma A over L times the absolute value of delta V. Now the way that I like to remember this expression is delta V equals IR. So I'm gonna move these things to the other side. L divided by A and 1 over the conductivity, and this is times I. Now delta V equals IR, so that means this will be the resistance 1 over sigma times L over A. Now here's where I'm gonna make the connection with what I told you at the beginning. I mentioned that the resistance R depends not only on the material but also on the geometry of the situation. And conductivity depends on the material that your object is made from. That's why the resistance R also depends on the material. But the resistance R also includes length and area, and this is the portion that I mentioned. It's referring to the geometry of the problem. So this is what is determined by the geometry of your situation, and this part over here is determined by the material. Okay, now remember, keep in mind what this is telling you. The longer the object is, okay, the more of it that you have, then the greater the resistance, which means the greater the potential difference that you will have between the two ends of your object. On the other hand, if you increase the area, the lower the resistance R is, then that means that the two potential potentials at the two ends of the object are going to have a potential that is closer to each other. And of course, there is a dependence on the conductivity. You can also write this expression, since 1 over the conductivity is equal to the resistivity, you can also see this expression for R as the resistivity times L over A. Keep my last point here. Keep in mind, okay, this specific expression that you do see in introductory physics is specific for this conductor, for this object, with the assumption that the current is flowing along this axis, this direction, and the electric field is uniform. Okay, I'm gonna show you now another example where we're gonna get a different expression for R. I do. Okay, let's move on to the next one. The approach is the same as the one that I did before. We will always start with this, and we will always be using the fundamental equation for potential difference, the minus in path integral of E dot dl, making the same assumption that the current is only due to the presence of an electric field. We have E dot dA. Now in this case though, the current and the electric field is not flowing in this direction. What I have here is I maintain some charge, let's say it's line charge density or charge per unit length on the cylinder, and then I create an electric field not in this direction but rather in this direction. And because the current density depends on the direction of the electric field, this means that your current is also flowing in the same direction. Okay, from at least conventional current, it's going to flow from the inner cylinder to the outer cylinder. Remember though, the actual direction of the flow of electrons is the opposite, right? Since it is in the majority of cases, it is electrons, the ones that are flowing, even though I indicate that the conventional current goes in this direction, in reality, it is electrons that are moving in the opposite direction. But in any case, we're going to forget about that for now. So this is the direction of the electric field. And I do also want to point out, when you calculate this integral, the E dot dA, okay, in the previous example, the area dA was here. Now we have to make sure we remember that this is going to be an area on the side of a cylinder. So this is gonna be, let me see if I can draw it here. So it will be something like this. Okay, your electric field or your current is flowing through the area, and this is just a small part of the side of the cylinder. It will not be here as it was on the previous example. Now, of course, there is one issue. I don't know what the electric field is, and in this case, since we have cylindrical symmetry, we know there are two ways that we can use to find the electric field. We can use Coulomb's law if we know the charge distribution, and you can always use that approach. If you have a problem with symmetry and you can use Gauss's law, then that will be by far the easiest way to get the electric field. And if you use Gauss's law with a cylindrical Gaussian surface, I will not do the example here, probably we have done it in the past, then this is gonna give us so I'll make a note from Gauss's law. and let's call this equation 1. When equation 1 is used here, where L, this side is the length L. Now, in a similar way with what I did before, now that we have I, the conventional current, in terms of these quantities, we can do as we did before, from initial to final E dot dl. And of course, this is the electric field, and this is going to give us I want to, before I move on, I also want to mention about dl again. Okay, dl now is going to be in this dimension, okay, from the cylinder, from the inner cylinder to the outer cylinder. I do want you to pay attention to the differences between the two cases. The vector, the small, infinitely small area vector dA here and here is not the same. The vector dl is not the same in the two cases when you calculate the path integral. Now this result will give us where B and A, those are the two radii of the cylinder. A, this will be A, and the bigger one is going to be B. And now, as before, when you have the relationship between I and delta V, you can, let's say, divide the two and see what cancels out and see what is left. But at the end of the day, let's call this equation 2, let's call this equation 3, and using equations 2 and 3, we'll get delta V equals I and now I want to remind you that delta V equals IR, as I said before, and this means that this is going to be your resistance. Now, the part that depends on the geometry is this one. And of course you have the conductivity here, and this shows you that your resistance depends on the material as well. But do pay attention. Okay, this will be R for this particular example where a potential difference, a constant potential difference is maintained between the two cylinders and current is flowing this way, whereas here it's a constant potential difference between these two ends of the cylinder and current is flowing that way. Okay, the resistance, what you get for R in these two problems is not the same. Obviously, they are not the same equation. However, it is true in both cases that the resistance R depends on the geometry and it depends on the material. But if you deal with current flowing in a situation that you're not familiar with and it doesn't look like something like this, then you will have to go through this process to see what is the expression for the resistance R. Now, what is the process that I used? I start with the definition of the current density, solve for the current I use the fundamental expression for delta V minus the path integral of E dot dl, and I get an expression, and then I combine the two to see how I and delta V are related. So that at the end, let's say, at the end, you are looking to find an expression of this form so that you can find R. So find delta V independently, find the current independently, and then combine the results of those two expressions to see what these are. And you should find it that it depends on the geometry and the material. And finally, again, I want to remind you, you do need to pay attention to what you will use for dA and what you will use for dL.